Hello, everybody. We're back again with another episode. And last time we talked about some physics, and so today we're going to be doing another lesson in physics. Last time we were talking about one-dimensional motion and the kinematic equations that you can use to kind of figure out the velocity, the position, or the acceleration of an object given some information. So we're going to extend our understanding of these equations and into two-dimensional motion, which is otherwise known as projectile motion, and we'll see what that means right now. Now we'll start off by looking at a particle's motion diagram in one dimension, just to kind of get a feel for the symbols and things like that we'll be using, as well as kind of an intro to what we'll be talking about. Here it is. So this is an example of a motion diagram of a particle. Now, when physicists say particle, they just mean object. So don't let that confuse you. As you can see at the bottom here, I've written an a sub x, and that equals 0 meters per second squared. That means that the acceleration in the x direction, or the acceleration in the horizontal direction, is going to be 0. That doesn't mean the particle isn't moving, however. It can mean that, but since the velocity is noted up here as 20 meters per second all the way through, that just means the velocity is staying the same. And in previous videos, or in the previous video, you can look and see that an object that has an unchanging velocity has an acceleration of 0. Hence why all of these arrows that I've drawn to represent the particle's motion are supposed to be the same size. So when we just saw that was one-dimensional motion is what we just looked at, and basically you saw this a sub x. That means in the horizontal direction. Well, when you throw an object like on Earth, it tends to trace out a parabolic trajectory. In other words, the path that it traces out is a parabola. In order to model this, we have to introduce a new component, which is called the y component. And I'll show you what I mean right now. So our second dimension is going to be up and down rather than horizontal. So this is our vertical component of velocity drawn in the arrows on the right. You notice that not all the arrows are the same size. In fact, it looks like as they go up, they shrink in their magnitude. And so this is because there is a downward acceleration experience denoted by this a sub y and the downward arrow. That acceleration is simply the force of gravity acting on an object as it reaches higher altitudes. In essence, since there is this downward acceleration, the velocity is in fact changing, and more specifically, the velocity is decreasing as it reaches the top of its path and then comes down again and lands to the ground. So what's happening here is that the object starts off with an initial velocity, but it slows down as it reaches the top of the path, and then it comes back down. And you might be able to see right now, as we combine the horizontal and vertical components, why this is going to form a parabola as it follows its trajectory through the air. So what we're going to take a look at now is going to be the components combined, the horizontal and the vertical components combined at the same time to create this parabolic trajectory that I've been talking about. Here it is. Okay, so an important thing to get started on in this is that during parabolic motion, the a sub x, the acceleration, is always going to be 0. That means that whatever speed that this is thrown in the x direction is going to remain constant throughout this entire path. So basically the horizontal velocity is going to remain constant, which is why I said right here that a sub x is 0 meters per second squared. However, this is not the case with a sub y. A sub y is causing the velocity in the vertical direction, as you can see in red. It's causing it to shrink, and then at the top, the vertical component basically just collapses, and all you have left is the horizontal component right there. But then, as it falls back and begins to accelerate towards the ground under the force of the acceleration of gravity, which happens to be 9.8 meters per second squared here on Earth, you will see this kind of interesting thing happen where the velocity increases back to where it was when it launched. And that's just the y component. So the y component changes and the x component does not. That's very important, and that will be very useful for solving some of these problems, which we'll get to later in this video. Okay, so the most important thing to understand about this projectile motion is that the horizontal motion remains constant when we're talking about projectile motion. The only thing that's changing is the vertical component of the velocity, because the acceleration of gravity is pulling downward, which is vertical, on that object. And there is no force other than the initial force acting in the horizontal direction. So, in essence, the horizontal velocity will stay constant and the vertical component will change according to gravity. Now, this is only true because we are neglecting a force called air drag, and we can get into that later in the video, but for now, and for all purposes of this video, we are going to neglect air drag. So with that said, I've drawn up two scenarios in which an object is given horizontal motion and another scenario in which it is not given any horizontal motion. And you'll understand if we are going to solve for the time that this object is in the air before it lands on the ground, the x component is simply irrelevant. The only thing that's changing is the velocity in the vertical direction. And let me show you what I mean. Okay, so here you can see I've drawn two different scenarios. One in which a ball is being shot out of a cannonball, and another in which a ball is being dropped just vertically down this 80-meter cliff. So the problem is the cliff is 80 meters tall. The ball is shot with a horizontal velocity of 12.5 meters per second. Now remember I said the horizontal velocity component stays constant throughout the path of the flight, therefore making it irrelevant when you're trying to solve for the amount of time that it's going to take, or the distance that it has traveled. So using this kinematic equation that relates distance and time, we can evaluate for different values of t. So what I'm going to do is just evaluate t equals 1 second, t equals 2 seconds, 3, and 4 seconds. And as you can see here, we have this kinematic equation that we discussed in the last video. This is distance equals the 1/2 gt squared. Plugging in different values for t, so after 0 seconds, essentially right when the ball is released from this person's hand, the ball has traveled 0 meters. Well, after 1 second, the ball has traveled 4.9. After 2, it's traveled 19.6. After 3 seconds, it's traveled 44.1, and after 4 seconds, it's traveled 78.4 meters. And so you notice that this is a non-linear thing happening here. This means that the distance is changing more than it would if it was just linear. So, or if the velocity was constant. But since we said that the vertical component of the velocity doesn't stay constant under the acceleration of gravity, and this just makes sense. Acceleration is just a change in velocity as time passes. So we'll look at the velocities first with this straight up vertical example. So after the first second, what this means is that, well, let's start at 0. At t equals 0, the ball is going 0 meters per second, and then after 1 second, the ball has increased its velocity to 9.8 meters per second. That makes sense. The acceleration of gravity on Earth is 9.8 meters per second every second. So with that said, then after 2 seconds, we double that number and we get it's going 19.6 meters per second. After 3 seconds, 29.4 meters per second. I'm just adding 9.8 meters per second every second that passes. And if we continue this pattern, we end up at the bottom with 39.2 meters per second at t equals 4 seconds. And if the cliff was 80 meters tall, that means that 78.4 meters is pretty close to 80, so it's essentially hit the ground after 4 seconds. And so you can see in this cannonball thing, the only difference is that there's an x component, but the x component does not determine how much time the object is in the air. You could fire this thing at any x horizontal velocity, and you would still get the same amount of time, given that you were firing this cannonball off of an 80-meter tall cliff. You can see here I drew the vectors out that would kind of show how this velocity in the y direction is changing. You can see just by the size of the arrows, their magnitudes are changing. And so that's basically the whole point of this, is that the velocity in the y direction is being accelerated while the velocity in the horizontal or x direction is staying constant. All right, so we've worked out the horizontal and the vertical components of the velocity, but that still says nothing about the speed of the particle in question. So what we're going to do is, since we have essentially the sides of a triangle minus the hypotenuse, we're going to use the Pythagorean theorem to calculate the speed of the particle, which is the magnitude of the velocity. And the magnitude can be found by applying this Pythagorean theorem. I'll show you exactly what I'm talking about right now. All right, so let's focus on this cannonball path now. As you can see from the last slide, I have drawn in the hypotenuse for each triangle that is formed by both the x and y component of the velocity as time passes at t equals 0 through 4 seconds. Now, we all know from our trigonometry class how to find the hypotenuse of a triangle given the length of the two sides. And so, what we can do is we apply the Pythagorean theorem, and we have these series of calculations here. Now, what we're looking at here is basically an x component and y component that make up the equation for this Pythagorean theorem. Notice now that the x component does not change. It stays at 12.5 meters per second all along the path of the projectile. That's the horizontal component. Like I've mentioned so many times before, that stays constant. But now look at the red. This is the vertical component of the velocity, and since it is being influenced by the gravity of Earth, it is changing. And that will give us the speed of the particle along this purple line here. Okay, so up until now, for the free fall object with no horizontal velocity, just the vertical component, we kind of manually came up with that. We just added 9.8 meters per second to the velocity each time a second had passed. Now I'm going to take a look at how to mathematically approach at the same final velocity just before the object hits the ground, using our kinematic equations that we talked about last time. Okay, so if you watched my previous video, you saw that the velocity function is just the derivative of the position function. And that's what I've written here. V of t equals d over dt s of t. That means the derivative of the position function. Now we have the position function right here. If we take the derivative of that, we end up using the power rule to derive the velocity function. As you can see, I've written out the power rule and just the steps that it takes. So if you don't know the power rule, review your Calculus 1, and that will give us the v of t equals gt. G in this case is 9.8 because the acceleration on Earth is just a constant 9.8 meters per second squared. Therefore, v of t equals gt. Now, you gotta wonder, what is the value for t? Okay, well, it turns out that because the position function is s equals 1/2 gt squared, that's indicative that t, using algebraic manipulation, is equal to the square root of 2s divided by g. And now, since we have the values for s and g, we can plug those values in. And I got that 78.4 meters from s of 4. That's the total distance that it fell. And so we plug that in and we end up getting 4 seconds. Now, back to the velocity function, now that we have time. We have the value for time now. So we plug in 4 for the velocity function. Remember, v of t equals gt. Well, that means that v of 4 equals the acceleration of gravity times the time, multiplied by the time that it fell. And you can see here I did a unit cancellation. You know that velocity is going to be in meters per second. This is a good way to check your calculations when you're doing these types of problems to make sure you're using the right formula. And so you do the arithmetic and you combine the units and you end up with 39.2 meters per second, which happens to be exactly what we got for a final velocity here at t equals 4 seconds. And so you can do it manually, or you can just use mathematics, and the elegance of it is just amazing. You can use mathematics to get your 39.2 meters per second as a final vertical velocity. All right, so now I'm just going to do a quick overview of everything that we covered today. Hopefully this will leave you with a great understanding of two-dimensional motion, as well as how it relates to the kinematic equations that we discussed in this video and the previous one. So let's check that out real quick. Okay, so we started this video by talking about two different scenarios in which we proved that the horizontal component of velocity is irrelevant when making these calculations, and that the y component of the velocity is changing. We then used the distance formula to evaluate the distance that the object had traveled given these values of time, 0 through 4. Once we got our vertical components and our horizontal component, which is constant, then we plugged those into the Pythagorean theorem to calculate the actual speed along this purple path. Now, to confirm our calculations, we used the kinematic equations, and we got the velocity equation. What we wanted to do was essentially get the final velocity before the object hit the ground, and we calculated that by taking the derivative of the position function, which left us with v of t equals gt. And then we found the value for t, which we got right here, 4, and we essentially manipulated the distance formula to get that right here, and we indeed got 4 seconds. By plugging in that value of 4 seconds to the v equals gt formula, we ended up getting the same result for velocity that we did when we manually calculated it. We calculated it by adding 9.8 meters per second every second that had passed. So if you guys enjoyed the video, just please like and subscribe for more physics lessons and lessons in aerospace engineering, or just any engineering material that you might encounter during your degree. So, like I said, I hope you enjoyed, and like and subscribe, and I will see you guys on the next episode of Aerospace Engineering with Brian McNulty. Thank you for watching.